Let's take a look at section 5.7, which is inverse trig functions. So that's our focus this week, is both differentiation and integration. And the good or bad news is it really is all about having these notes in front of you. I don't expect you, at least in my class, to memorize what the limits of integration would be or what these functions would be. So just have them handy and ready in front of you. Maybe make yourself a handout. There might even be a handout in your OneNote notebook. It's really going to help you through these last two sections. So there's really just two videos this week. It looks like 3 videos, but this guy is actually tied in here. This is just a good handout. So when I said there might be a great handout in your OneNote notebook, that's what I'm talking about, the basic differentiation rules that will include all of the rules that we're going to talk about. So the first thing we'll do is develop the properties of the 6 trig functions, and then we'll differentiate them, differentiate an inverse trig function. So essentially we have the 6 trig functions that we already know, and we know how to find the derivative of each of them. We've talked about that way back, I think, in chapter 1 or chapter 2. Now we're talking about having the inverse, and what I'm going to want to do is to find the derivative of the inverse of the function. Now, we know to have an inverse, our function needs to be monotonic, and none of our trig functions are monotonic. So how do we get around that? Well, let's take a look at what is the sine function. The sine function essentially looks like this. Hopefully we know that. It's periodic. That was really bad, but you get the idea. I'm not an artist. I'm a mathematician and an educator. So this is basically the sine function. And what I'm looking at is, obviously this is 0, and this guy is pi. And what I would look at is restricting the domain from, say, pi over 2 to 3 pi over 2. Now, what would that do for me? Well, from this interval, within this interval, this is a strictly monotonic function. It is decreasing over the entire interval. So that's what we're going to be doing when we're looking at the inverse trig functions, and that's the part that, again, hopefully your professor, if you're not in my class, doesn't make you memorize, but if you are in my class, I won't make you memorize it. This is what we're going to be doing, is looking at what do we have to restrict the domain to in order to make this work. So again, here is a great handout for you, and this will help us, keeping in mind that this is an inverse trig function. So what we just looked at was arc sine. Well, we were looking at the sine function. Now I'm looking at the inverse sine function, and I had used pi over 2 to 3 pi over 2, but instead they're just saying, instead of using this part, let's go back and look at negative pi over 2 to pi over 2 for y. Now why is it y? Because again, this is the inverse, so these are now backwards. The domain will go from negative 1 to 1, which makes sense, because in my original function, my y's, my range, went from negative 1 to 1 because it oscillated between those two values. So again, keep in mind, I'm always talking about the inverse. I'm not going to go through each of these. Again, this is something that I would just have handy in front of you. If you can start to memorize them, that's great, but again, for my class, you won't have to. So again, this is just a great visual, so I can see what the inverse sine, which we call arc sine, what that function looks like, inverse cosine, inverse tangent, etc. And it again lists the domain and the range. So it's really the same as the last slide that I showed you, but here is a great visual. I would have one of these in front of you at all times while you're working through this section. So again, this is the unit circle. Dear God in heaven, if you don't have part of this in your brain by now, I don't know where I failed you, but I apologize. But you should know the unit circle, and if not, then have it in front of you at all times. So again, memorize it would be a good idea so that you're not always referring back to it. But keep in mind that all of the values are in the cosine of x, comma, sine of x format. So what that means is cosine of 0 is 1, and sine of 0 equals 0, which I can see here, because this is the point 0, and I'm plugging it in and finding that 1, 0 is the solution. So cosine of 0 is 1, sine of 0 is 0. We get the idea. It continues around. Notice I have both radians and degrees. We focus on radians, of course, in this class. So that's really what we're looking at. So let's take a look at how we're going to evaluate a function like arc sine of -1/2. Well, first of all, I want you to think of it like a function, y equals arc sine of -1/2. Then I want you to think about what we know about inverses. Inverses undo one another. So that means I could take the sine of this, and sine and arc sine are inverses, and they will therefore cancel each other out. And so on this side, it would make sense to then take the sine of y, because it was y equals, and now it's taking the sine of each side. So that's where I am right here. Sine and arc sine will cancel, giving me -1/2. On the left, I have sine of y. Now, again, using my unit circle, I can look for what values will give me -1/2. So notice I've listed quite a few of them. -5 pi over 6, -pi over 6, 7 pi over 6, etc. And hopefully we know, again, that I can just keep going and going and going in that pattern. Then, this is the part where you need that other handout. I need to choose any of those values that I've listed that fall within the restricted domain. And that would give me only that y is -pi over 6. So that would be my solution. So using that same format or that same process, again, keeping in mind that you'll want that handout in front of you so that when I get to the end, I can check what the range was for my function. Because it's y equals, I'm checking the range. I want you to follow that same process, and when you're done, press play to see how you did. So again, for the first one, because it's arc cosine, I'm going to take the cosine of each side. So the cosine of this side is cosine of y. The cosine of arc cosine goes away, and I just get 0. So I'm saying, for what values of y do I get 0? So cosine of what values are 0? Notice I've listed several. This was the range of my function, my arc cosine function. 0 is less than or equal to y is less than or equal to pi. Which of those are between 0 and pi? Just pi over 2, so that's my solution. Same thing for arc tangent. Again, I'm just going to take tan of each side, because on the right side it'll cancel and just give me radical 3. Then I get tan y equals radical 3. Use the unit circle to come up with some values that will work. Use the range of my function to determine which of those values are in the required range, and the only one that works is pi over 3. So one thing to keep in mind as we move forward is that restricted domain is super duper important. For instance, if I took the arc sine of pi, you would think that my answer is pi, which would make perfect sense. But we already knew this property that says x has to be between -1 and 1, and then y has to be between -pi over 2 and pi over 2. So pi is not in there. So my solution would be 0 and not pi, because the sine of pi is 0, and that's what it's going to equal, because it has to be in the restricted domain and range. So again, something to keep in mind as we're moving forward. Make sure that you know those restricted domains and ranges as we're solving. So let's take a look at how to solve an equation. So before, it wasn't an equation, we were just looking at the expression, and we just added the y in there just for fun, essentially. Now we're actually solving. So as expected, to get rid of arctangent, or the inverse of tangent, I would write the tangent of each side. So the tangent, arctangent, that guy's going to cancel and give me 2x minus 3. Tangent of pi over 4, which I will then turn into 1 using my calculator or my unit circle. And so I get 2x minus 3 equals 1, and now it's just an algebraic equation that I can solve very easily. Most often you will get a question like this. So this question uses inverse trig functions. It also uses the fact that trig functions have everything to do with a right triangle. So let's break this one down step by step. I am given that y equals arcsine of x. I want to find the cosine of y. So the way that I have found it's easiest to do this is to make a right triangle. So the first thing I'm going to do is I really want to get, whatever I can by itself. So the same way that I would have previously, I'm going to say sine of y is equal to sine of arcsine of x. And that would give me sine y equals x. So that part we've done like 100 times now. We're pretty good at it. Well, now let's talk about a right triangle. And we're talking about sine. Well, what I know about sine is that it's the opposite side over the hypotenuse. So hopefully you remember that from when you took trigonometry. So opposite side meaning the opposite side to whatever angle it is that I'm referring to. So if you'll notice, and this I'm actually going to call it sine of y because that's what I have up here. If you'll notice, that means that I need to build a triangle so that the side opposite angle y, and I, yes, randomly selected one of the two acute angles to call y, because it doesn't matter which one I choose as long as I keep it consistent throughout the question. I know that sine, which is opposite over hypotenuse, must equal x. So notice what I've done is I've called the opposite side x, and I've called the hypotenuse 1, because x divided by 1 is x, and so it fits this description. So that might not make sense to you as to why I'm doing that yet, but it will in just a moment. So far, I have explained y, because I said this is going to be angle y. I've explained x, and I've explained 1. And I'm going to call this guy any other letter. So I'm not super creative. I'm calling it b, because one side's a, one side's b. You get the idea. So I replaced a with x because x fit into my equation. But why do I need something for that side b? Because it says find cosine of y. Well, what do I know about cosine of y? Well, cosine of y is the adjacent side over the hypotenuse. And so essentially, the side adjacent to this is b, and the hypotenuse is 1. But I can't just say, okay, it's b over 1, because what's b? I need to write b in terms of x or y. So that's where this math is going to come in. So that brings us right here. What I'm looking for now is essentially to use the Pythagorean theorem that says leg squared, which is x squared, plus leg squared equals hypotenuse squared. So notice that's what I did here. X squared plus b squared equals 1 squared. Now what I'm trying to do is obviously solve for b, because I don't want it to be b. I want it to be something in terms of x or y. And of course it's going to be x, because x is the side of the length of the side. So I'm subtracting x squared from each side, which gives me b squared equals 1 minus x squared. I'm taking the square root of b squared, which gives me b. I'm taking the square root of this whole expression, which gives me that whole expression. So this guy is in fact the square root of 1 minus x squared. If I want to find the cosine of y, I'm then replacing b with 1 minus x squared over 1, because that was the hypotenuse. And notice that is my solution. Cosine of y equals the square root of 1 minus x squared. So it has everything to do with just drawing yourself a triangle and using the Pythagorean theorem. So here's one for you to do on your own. This is a little bit different than the last one that we just did. Notice this is not an equation anymore. It's saying find the secant of the arc cotangent x over 3. We're still going to use a right triangle to help us to do this. So do your best. Try this one on your own. When you're done, press play to see how you did. Again, I always suggest drawing yourself a picture of a right triangle. And I'm going to write it kind of small because I have my real big picture below to the right, which I'll uncover in just a second. But choose some angle to be y, because really I can say equals y. So choose some angle to be y. So if I'm looking at arc cotangent, remember that tangent is opposite over adjacent. So the inverse of that is adjacent over opposite. Cotangent would be adjacent over opposite. So if adjacent over opposite is x over 3, that means this is like an x and this is like a 3. Oh, just kidding. That's the hypotenuse. And this is like a 3. So that's where my picture would start. Okay, notice it's the same as I have here. I've labeled it theta here. It doesn't matter if it's theta or if it's y. It's the same thing. Now what am I trying to do? I'm trying to find the missing side, which is the hypotenuse, and I need it because I need it for secant. And secant of y is the hypotenuse over adjacent, because cosine is adjacent over hypotenuse and secant is the inverse of that. So how do I do that? Well, that means I need to find the hypotenuse in terms of x instead of just h. So again, just like I did on my last question, I'm going to say leg squared plus leg squared equals hypotenuse squared. I'm solving for the hypotenuse because I need that to plug into my secant formula. So I get the square root of x squared plus 9 for h. So why is that important? Because now I'm going to just take this and say secant of theta or y, it doesn't matter, I used y up here, I used theta down here, same idea, is the hypotenuse, which is x squared plus 9, divided by the adjacent side, which of course is x. So that is my solution.